Swayam Prabha. Digital India. Educated India.
Okay, two effects that I said we will discuss in this class are these. Ground effect on control force requirement or the stick force requirement, and other one is in maneuver what happens. Okay. So, force requirement and maneuvers or elevator deflection requirement, right. So, of course, if you remember, we said that ground effect will only take place when we are trying to land, right, and when you are trying to land you are actually trying to slow down, right. How do you slow down? Increase the angle of attack, right. Perfect landing is when you are landing at stall, landing at touching down at stall is the perfect landing condition. So, ground effect will take place or let us say I will say ground effect while landing. Two things which can happen. We said that downwash is going to be less, right, much less, and that is going to reduce this quantity, isn't it, right, and when this quantity reduces then this location is goes aft, right. So, if this was my x and p in air, okay, with no ground effect, then the new x and p will lie somewhere here. Close to ground, okay. So, I will write this no ground effect and ground effect, GE for ground effect, right. So, if your CG is fixed, what is increasing because of this? Static margin. So, stability is more, right, and look at this picture. So, you are able to trim at some angle of attack in air, right. This is alpha trim, this is no ground effect, right. No ground effect. What happens when I am including the ground effect in this? This curve will have steeper slope, right. So, that means you have to make up for this extra delta Cm to trim at this alpha, isn't it? And that will require what? I am trying to make up for this delta Cm, right? This is with ground effect, right? So I have to make up for this delta Cm to trim at this alpha, right? What you have to do? Yeah, we are trimming, right? We always trim. Isn't it? We are trying to make up for this delta Cm, which has happened because of the ground effect. What is going to change? What we have to do? We have to apply more elevator deflection, right? In which direction? Which direction? So you are at some alpha, right? Let's say elevator alpha is positive, so elevator deflection is up, isn't it? Now you want to make up for this. You have to move your elevator further up, isn't it? Because you want to create a pitch up moment. All right. So elevator deflection right. It's also clear from this trimming condition, isn't it? If I want to keep this alpha fixed, Cm alpha has gone up, so I will need more delta E, right? More delta E up. All right. What is the second effect? So there is one effect. What is the second effect? Remember, we are talking about only one effect so far. There is the derivative of the downwash angle with respect to angle of attack, right? What is the other effect? Yeah, lift will,
because the loop is closed,
right,
so the circulation changes.
epsilon naught. No, this epsilon has two terms, right? Right. So angle of attack at the tail is also going to increase, and what happens because of that? Let's say elevator is fixed at some point, right, and then you have this epsilon naught which is increasing the angle of attack at the tail, right. So there is a, I am getting elevator up means more lift downward, that is giving me a pitch up moment, because of which I am getting different alpha trims, right. More angle of attack is when elevator is up and the lift produced at the tail is down, isn't it? Now because of this term which disappears when you are close to ground, angle of attack at the tail is going to increase, right. Right, and that small delta LT, right, is going to create a downward pitching moment. So, further elevator up you require, isn't it. So, in both the situations, right, combined effect is that you have to, you need more and more elevator to change the or to maintain the same angle of attack, and also to, if you want to change the velocity, when you are landing speed has to be lower, isn't it. So, you are on approach with some velocity, and then when you are trying to land, this speed has to go to further small, actually it should be V stall, right, into some factor. So, more and more elevator, and this is up all the time, because when I am landing I have to maintain this alpha which is close to alpha stall. We want to see the plot how elevator deflection requirement changes. For level flight. Trim at constant speed. Okay, let us talk about only level flight trim condition, and then let us plot the effect of the ground effect, right. And I am plotting this against x C g over C bar. So, typically this the x C g is this plot where the textbook from where I have got this plot, they are measuring x C g from the wing aerodynamics center. Okay. So, this C g is measured So this is these two should be parallel. Okay. So this plot is the plot of elevator required to trim the airplane in level flying condition, okay, at constant speed, right, with respect to the CG location. So no G, G, right. How will the plot for stick force gradient will look like? Qualitatively it will look something like this, same as this, right, because the elevator is directly related to the stick force, right. So we are going to apply the stick force and the corresponding elevator deflection we see, right. So this is the effect of the proximity of ground when the aircraft is trying to take off or trying to land, right. Let us look at another effect, and that is maneuver. What happens in maneuvers? So what is a maneuver? Maneuver is when you are trying to even landing is a maneuver, okay. So any flight will be called maneuver, but here in this we are talking about the case when the rates are also involved, right. So there are maneuvers where rates are all fixed, right. Steady state maneuvers, for example, level flight condition, all the rates are 0, right. Even in landing the rates are all 0, right, and taking off, but there are maneuvers where rates are not 0. So for example, there is one maneuver which is called pull up maneuver, okay. What all I need to have for this aircraft to pull up? So you want to create an acceleration, no? A normal acceleration upward, which should be equal to, so there is a weight and this is your lift L, right. So you can pull you can do this maneuver only when the lift is going to be more than the weight, right, that is clear, and that ratio is called the load factor, right. So if I want to write down an expression for this n, and let us say I want to do a pull up maneuver, this is signifying the G factor, right. So 1 G is pulling 1 G maneuver, which is the case when you are flying level flight condition. Any other value of n greater than 1 will also give you a normal acceleration, right. So what is this n? N is L minus W, right, over m, if m is the mass of the aircraft. And W is equal to mg, right. So this is so there is a normal acceleration in any maneuver. And also say that this radius is r of this loop, and how it's happening? How it's happening? How you are able to pull up? So you are trying to apply the elevator so that you can create a pitch rate, right, and that is going to take this up, right, and you can do it at constant velocity. So let us say velocity is constant, okay. It's happening because of this pitch rate, right. What is this pitch rate? Is 2 pi so that is like a distance, right. 2 pi is the angular displacement over time, right. Correct. I can also write this q in terms of this acceleration, and that is right, centripetal acceleration is this. Pull up maneuver at constant velocity, right, at this load factor, this is how pitch rate is related to the load factor and the velocity. Okay. What this pitch rate is going to do to the aircraft? Now I am trying to rotate the aircraft, right. What is it going to do? Now I have to find out the control requirement, right. That is what we are discussing, longitudinal control. So in such a maneuver, what is happening when we are pitching the aircraft?
Connect the lift to the sticker.
No, delta E is there. Delta E is going to give a pitch rate. Yes. that is all right. Any other thing? Anything else happening because of this pitch rate?
Drag is the velocity will be along the same a component of thrust will start balancing the
Angle of attack.
Angle of attack? Where?
what time only the elevator will change. Don't change anywhere else.
Angle of attack is going to change. Where? Let's say I'm giving a delta E which is causing a pitch rate, right? Because of that, what is changing? Angle of attack is the right answer. Where is changing? In what ways? So you are creating a moment about this CG which is pitching up positive Q, right? And let's look at what is happening to the flow at the tail. Okay, so I'll draw it as a symmetric airfoil. What is it going to do? So when you are pitching the aircraft is, this tail is going to see a relative velocity upward, isn't it? Right? Do you see that? The aircraft is pitching up, right? So tail is going down and tail is going to push the air down. So relative air that is coming onto the tail is going to increase, isn't it?
But even in the aircraft change, the flow velocity is anyway going to be facing the aircraft. So where is the additional landing effect? The flow is going to face the leading edge of the aircraft and it is going to be parallel to it as well. How is the angle of attack changing to this?
But that is changing. Velocity is still.
No, velocity will be parallel to the thrust. Velocity will be parallel to the thrust.
Let's say aircraft is flying trim, this level trim condition, okay, and now you want to initiate a pitch up, right? So what you are going to do? You are going to apply elevator up, right, and that's going to, so that Q, no, how much Q you want, depending on that you will deflect elevator, right. Afterwards what happens, this starts going down, right. If this, so earlier it was only having this velocity which was forward velocity, let's say V, right. Yes.
Goes even in slow motion, it will be perpendicular to the edge. I mean, to this thing.
What are you saying?
I'm saying that if you fix an elevator, even the elevator will go in slow motion. I mean, we'll have to.
So you're saying the angle of attack changing due to the changing camber?
Yeah.
No, this is not due to the camber. This is only due to the pitch rate. This is only due to the pitch rate. Yeah. Camber is not. I am not saying the camber is changing. Okay, I deflected the elevator. Afterwards, I see a pitch rate, and then because of that pitch rate, this elevator, this tail starts pushing air down. So you see a relative air upward, and because of that, the angle of attack at the tail is changed, right?
VH will change. The horizontal velocity. Sorry, VV.
Yeah, right. Vertical component of velocity will change, which was not there, right. So what is that velocity? Let's say I call this W, Q into LT, right. So, delta alpha is going to be let us say this is U naught, right. Is it all right? You see that it is going to change only in this maneuver, right. So, what will happen to the stick force now? So, Fs is now I am writing this modified alpha t, right, and this will include the effect of the pitching. And I want to replace this Q by this quantity, so that I directly have a relation between the stick force and the load factor, right. While you are doing that, you should also non-dimensionalize it. Okay. So, this is how the rate is non-dimensionalized. Right, there is a non-dimensional pitch rate. Okay. So, I am calling this U naught. So, U naught is actually equal to V, right. So, V is equal to U naught. So, n minus 1 over G into 2 So, if you remember, I wrote this expression for Fs at, so this is pitch control force required pitch control force required at constant speed and constant normal acceleration, right, and this normal acceleration will depend upon the load factor that we are trying to overcome, right. This is above the level flight condition, right. So, more than 1 g, whatever that normal acceleration is, in terms of aircraft parameters. I wrote this expression in the last class, and we also found the control force gradient. And the control force per g, that is given by this. Both C1 and C2 are functions of all derivatives of aircraft. We have seen aerodynamic derivatives, right? We have seen control derivatives Cm delta E, stability derivative Cm alpha, and there is one more derivative which is damping derivative. Okay. So, now if you want to look at the trim condition, which is Cm Cg is equal to 0, that will have one more term, and that is this Cmq, okay, and Cmq is the damping derivative. Stability, damping, control. Right. Now, let us say I want to find out what is the elevator requirement for per g, okay, how much elevator I need to get the normal acceleration, that also can be found out. And so, there are two conditions, one is equation 1, and the second one is this has to be equal to, this is the lift coefficient, right, and this is equal to, lift is equal to n w, right. So whenever you have a rate involved, okay, there will be damping created, right? Air will also try to damp out the motion.
Something like friction.
In the post stall regime of flight, it will be linear. Okay, we are in this whole course we are actually talking about pre-stall conditions, right? It may not be linear in the post-stall angle of attack. Okay, so if you solve 1 and 2, you can find out what is elevator required for the normal acceleration that you want, right, and that is given by this derivative. Remember this these terms C1 and C2, they are not constants, okay, they are depending upon derivatives. So I also put a bar here because I am talking about which one? Yeah, if I want to let's say, see, the unit of each of these terms should be a constant, right? So that is how you have to look at it. Okay. So small delta d delta E over d, and what does it mean? Small elevator deflection required to create large acceleration, right? Isn't it? But such an aircraft will not be easy to fly. You deflect elevator a little bit and it gives you a large acceleration. So it's not easy to fly such an aircraft. Small right. So such an aircraft is not easy to handle, it is not desired. Yeah. Minus of this whole term. So this is also called elevator angle per G. Location of the CG when this becomes 0 gives you what is called stick fixed maneuver point. Right, there is a CM alpha term sitting here. which is related to x CG minus something, right. So, location of CG when this term becomes 0, that is the point which is called stick fixed maneuver point. Location of CG where do you think this will lie? So, I will quickly give you an expression for MP is for maneuver point. Okay. This quantity is usually positive, okay, and CMQ, what should it be? Positive damping means what? Air is going to offer some damping when you are trying to rotate the aircraft, right. So, what should this quantity be? This should be negative. Think about it, how we are writing the equation. We are writing equation as m equal to and so on, right. So, there will be a term like IQ dot, right. So, if you bring this to this side, it becomes, right, and for positive damping you should have CMQ which is negative, right. So, this maneuver point actually lies behind the neutral point, right. That is what it means. You have this part which is positive, right. So, XMP which is the maneuver point is lying behind the neutral point location, right. What does it mean? You can be unstable, but still you can maneuver, isn't it? So, marginal stability case when your CG is lying very close to the stick fixed neutral point, you can still maneuver because in maneuver you have increased stability, right. Okay, we will stop at this point. Okay.